Chucky. Okay. Okay. Oh, and we're live on YouTube. They're sharing the screen. Can people see the slides? Or the slide at the moment? Yep, great. Okay. So, welcome to this PLUMED Masterclass. This is Masterclass number 6 on dimensionality reduction. And let's just remind you a little bit about where this is coming from. So there should be, let's first of all just check in with everyone. So does everyone see a slide with some dogs there? Okay, so basically just post in the chat, like in terms of how are you feeling, which dog are you feeling most like? Are you feeling like tired, number 1 dog, or are you feeling full of beans, number 9 dog? I nicked this off someone else. I thought it was quite cool. I don't seem to be able to open the chat. There's one thing I don't like about these sharing things is that you can't. There we are. Okay, so we've got some variations. So one person feeling very number 1. Oh dear. So we've got 2, 3, 7s, a 2, a 1, a 3, 5, 6. If I were very clever and good at maths, there's quite a few people who are being very honest and saying they're at number 1. It is just after Easter, maybe they're full of chocolate. But I would probably say, okay, so to me, it looks like we're averaging around 4. So let's hope that we could make that a little bit more active by the end of this session. Okay, so just to remind you what PLUMED is, I'm just going to exit my slides for a moment, and because I can't close the chat, and then I'll go back. So PLUMED is this open source, free available C++ library. It's developed by the 4 of us, Giovanni, who was on here briefly, Max, who is normally here but isn't here today, Carlo, who has never been here, and me, Gareth. It's in C++. It does these enhanced sampling methods. We've now had some experience of learning about 2 of these enhanced sampling methods, umbrella sampling and metadynamics. You've also done a little bit about replica methods, so we can do multiple replicas. And we can do this analysis of MD data. We can also do all our error bars, hopefully. So that's what we've covered. So today, the title of the talk is Notionally Dimensionality Reduction, but when I was writing the exercises, I thought I would expand that out a bit and come into this question that we're asked quite regularly, and that is critical to using these methods now to actually do something. This question of what CV should I use? So what's the appropriate CV to use for the calculation that you're running? And so what I'm hoping is that during the week, as you work through the exercises, you can explore some of the options. I will explain some of the options as to what you might do with CVs here. And perhaps next Monday, when we come for this follow-up session, we can do something a little bit more interactive where we talk about the particular problems that you're looking at and we think together about the sorts of CVs that you use for these simulations. Okay, so in this quick talk, I'm going to try and give my answer to this question of what CV should you use, which I think might be an unsatisfactory answer, but hopefully it will at least give you some insight and it will give you some idea of where I'm coming from with the exercises. I'm going to skip over a lot of details with methods. I'm going to go through things very quickly because I'm going to cover a lot of sort of ground of different theory of different CVs. Hopefully there are resources provided through the tutorial that should help you. If you're particularly interested in one topic, you can take that further. Okay, so without further ado then, let's get into this question of what CV should you use. So let's talk about why this idea of dimensionality reduction is connected to this question of what CV should I use. And what I've got here is an illustration of the sorts of problems that we solve when we do these molecular dynamics, metadynamics, or whatever it is. Okay, so what I've got here is a two-dimensional free energy surface, and I'm studying the dynamics of that two-dimensional free energy surface. And this is a representation of what we will call phase space, okay? And phase space is basically all the coordinates that the positions are allowed to take. So in reality, phase space is a much higher, when we do a simulation, phase space is a much higher dimensionality object, okay? Much higher than 2 dimensions. And we want to reduce it down to some lower dimensional thing so that we can visualize it and see it. So in this simple 2D example, there are lots of different ways that we can do this dimensionality reduction process. And I've got 2 examples here. So what I've got here is basically the logarithm of the marginal probability distribution, and that's what we call the free energy surface. So basically, when we calculate the free energy surface here, what we've done is we've integrated out the other direction. Okay? Now, if we think about our free energy, and that's what we're doing every time we calculate a free energy surface. So we have this phase space, which is this high dimensional object with many different coordinates that can read, and we integrate down to a lower number of dimensions. Karen, you've got your hand up.
Yes, I have a question. I don't know
Yep.
if it's the right moment to,
yeah,
to ask,
go.
but do you know what is the difference between a collected variable, reaction coordinate, and an order parameter? Is there any difference?
Can I come back to that answer?
Okay, no problem.
I will try and cover that during the talk.
Okay, thank you.
Okay, fantastic. But it's a good question. Okay, so but in all 3 cases, we have some phase space, and we integrate out, and we get some free energy as a function of some coordinate or other. So we've got a high dimensional object, we go to a lower dimensional object so we can visualize. Okay, so if we think about these free energy surfaces that we can calculate, I've got 2 examples on that diagram. This one at the top is what I would call a boring free energy surface. It's got a single minimum, and there's not much along that direction, okay? This one over here is an exciting free energy surface because it's got multiple minimums, so we've got metastability here. So normally what we'd be wanting to do is integrate out the boring directions, the directions where there's no minima, there's no metastable states, and have the free energy as a function of the interesting directions, the directions where we have multiple minima and metastable states. Okay, so that's sort of the objective. Now, how can we do that? What sort of CVs can we use? Well, in this example here, we can use just one of these coordinates, like this one here. So the free energy surface that I've labeled as boring, what I've done is I've used that arrow, that's the coordinate that I've used to construct that free energy landscape. And then I can use any linear combination of these coordinates that define phase space. So that means any rotation of that arrow there. And those are all valid collective variables that I can use. And as you can see, as we rotate around 90 degrees, that free energy surface gets progressively more and more interesting. And in some directions, we'll be able to see the 2 different distinct minima, and in other directions, we won't. Okay, so those are all the sort of linear CVs that you can use, but you can also use nonlinear CVs. So a nonlinear CV would look something like this, some sort of curved path in space. So any curved path in that phase space, we can use as a collective variable for these problems. Okay, and if you think about those things that I've shown you, there is an infinite number of the linear collective variables. There are an infinite number of linear combinations that I can form of these basis vectors, and there is also an infinite number of nonlinear combinations that I can form of these basis vectors. So I really have huge amounts of choice. So how do I begin making this choice? Well, I think there's 3 strategies that you can adopt. So the first is that you can think about the physics that you're studying and find some suitable descriptor on which you believe that there will be those metastable configurations, so that you see those distinctions between different structures and calculate the relative free energies of them. Okay, so that's the first way that you can do that. So you use your knowledge of the problem to think of a suitable descriptor. The second method that you can use, which is sort of related to that first one, is to think about the symmetry of the problem. Okay, so this is particularly important if you're studying something like nucleation of a solid. You know that all the atoms are equivalent, so your CV should somehow incorporate that symmetry information within it. Okay, and it should reflect those symmetries that you know about the problem. So those symmetries represent a useful way of thinking about the descriptor. And then the third approach that's appearing more and more in the literature is to adopt some sort of machine learning algorithm to find the CVs for you. And I have to be honest, I have a little bit of a love-hate relationship with these machine learning approaches. I'm going to explain a little bit why I have that love-hate relationship with them. So there's lots of people who think that this is basically the way to solve these problems, that these machine learning algorithms, they're fantastic, and there's a lot of concern both sort of in the scientific community about using these algorithms to basically solve many problems, also in the social sciences and so on and so forth. And I think that's slightly overblown, that concern. And I'm going to explain why. Okay, so people who make this argument will say things like, the issue of finding the CV is a chicken and egg problem, in that, okay, the egg is a suitable CV to bias. So we want to find this CV, and that's going to be our egg. But to know what the best CV is, especially in the way that I presented it, we need to know where those metastable states are. So to find an appropriate CV, what we really need is a converged free energy surface. And so we've got this chicken egg problem because we need to know the CV in order to get the converged free energy surface, but we need the conserved free energy surface in order to find the appropriate CV. And there are some arguments in the literature, and I may have also put these arguments out there, which I now no longer believe, that machine learning offers a solution to this, because by using these wonderful machine learning algorithms, that you will basically solve this program iteratively. You'll find the CV, you'll converge the free energy surface, and the machine learning will do everything for you. And I'm not 100% convinced by that argument anymore, because the problem I have with machine learning is that what drops out of a machine learning algorithm is not a nice CV that you understand. It's not that egg. What comes out is a cake. And sometimes cakes have egg in them, but sometimes they're also vegan cakes. Okay? So there's a danger that you go off, you do all this machine learning stuff, and you get out something that you don't really understand at the end of the problem. And if you don't really understand it, there's a good chance that you'll kill the chicken whilst you're at it. So someone's got their hand up, yes.
Hi, it's me. Can you start with the bad CV selection and then get a surface and start from this point on?
Yeah, you can start with, I mean, this is a good way to start with these things, is you start with some bad CV, you then see what doesn't work, and then you refine. But the point I want to make, and the point that I'm sort of getting to, is that the CV is important because it's what's going to give you your understanding of the problem. And so, you know, you have to come up with a research question that you're trying to answer. Machine learning algorithm is never going to do that for you. We're in the business of science because we want to construct meaning. We want to understand what's going on. We don't want the computer to understand. We want us human beings with our feeble carbon minds, as opposed to these silicon minds, to understand these problems. Does that sort of answer the question?
Can I ask another question?
Yes, yeah.
So after we run a bias simulation, we can always reweight into whatever CV we want. So wouldn't it be a suitable, a reasonable argument to argue that you can have these machine learning algorithms find a CV that you maybe don't understand, but to bias that, and then reweight it into something that you can understand?
Absolutely. But the important thing is that before you've come up with this, you've come up with the CV that you're going to understand, that you've come up with the research question. That you're not just saying, I'm going to apply this machine learning and I'm going to understand this particular physical system, because I don't think that's going to happen. You need to come up with those questions. You need to come up with that question of what is it that you're trying to understand? What will it look like if these simulations work? What will I understand that I didn't understand before? And that's, this is the point that I'm trying to get. You know, all these discussions in the abstract of what a CV is, they're really not helpful. You know what systems you're studying, what physical systems they are. You know what questions that you're trying to answer. So you have to think about those systems and work out what it is that you're trying to understand, and in that way construct your CV. And I think this is more and more important. So if we think, the only way to come up with a CV, I think, is to think about what research question you are trying to answer. And I think the more we see these machine learning algorithms make an impact on this field, the more important this question is going to come. This question is not going to be made easier by the advent of these machine learning methods. This question is going to be made more important, okay? Once you have that research question, then sure, the machine learning will help you refine that question and come up with a good way of sampling. But if you don't have that physical understanding and that understanding of what question you're trying to answer, you will get nowhere. And ultimately, that should be an exciting thing, because, you know, none of us got into science to turn handles and get out results. We got into science, I hope, to understand the physical world, or a representation of the physical world on a computer. And so, you know, thinking about those research questions and thinking about what it is you want to know, it should excite you, and it should be what motivates you. Does that, whoever asked the question, does that answer that one?
Yes. So okay. I guess I said it myself. If you want to reweight into something, yeah, you have to know what that is.
You have to know what it is you're going to reweight into. I mean, you don't have to necessarily bias the CV that's going to give you that physical insight. And it may not even be the right thing to do to bias that CV. But you will need a free energy that is a function of that CV, because that's what's going to provide you that understanding. That's what's going to allow, you know, the CV as a function of whatever it is what's going to allow you to publish that paper, which says something. Yeah. Okay. So that's sort of my overarching unsatisfactory view of this question of collective variables. So now I'm going to tell you a little bit about what's in the exercise and what I'm showing you. It's a bit of a mishmash of things. for the reasons that I've kind of explained in these previous slides, is that there isn't just one answer to this question of what is an appropriate collective variable. So the first thing that you're going to see in the exercises is how to use Plumed as if it's just a Python library. I think this is really useful. It's a nice little feature. I like working with Python notebooks a lot. So I think the ability to call Plumed and get those results into a sort of Python readable format is a really nice thing. You can also, if you don't want to use the Plumed tools like SumHills, you can get the output from Plumed and then implement your own SumHills in Python if that's what you want to do. Similarly with reweighting and so on and so forth. So I'm not going to talk too much about that. It's explained in the exercise and you can have a go at that. So then the next thing I've shown you is, so the group of Michele Ceriotti has this nice tool called Chemiscope that allows you to visualize chemical structures and sort of CV plots side by side here. So here what I've got is a protein structure and I've calculated 2 collective variables there. And each of the points in the plane on the left of that figure is one of the configurations. The point that's shown in red is the configuration that's shown on the right. And if I play the movie of the trajectory movie, I can see whereabouts in CV space each of those structures is projected. So I'm going to show you, so the exercises show you how you can build, use Plumed to construct these Chemiscope representations. You then load to and everything's within a web browser, so you don't need to use VMD or anything. Once you've got this Chemiscope representation, you just load it onto a server, and then you can visualize what your CVs, where these configurations are projected in CV space. So that's quite a nice little tool that you can use. So those are a couple of nice tools that you can use to understand CVs that you're working on and thinking about using. So then I'm going to show you some linear dimensionality reduction methods. You don't need to do all of these exercises. If you're not interested in one in particular, then by all means skip it. So when I think about these linear dimensionality reduction methods, I'm thinking about methods, the methods known as MDS and PCA. Okay, both of these are implemented within Plumed. And the way that I like to think about these is I think in terms of there being 3 ways of representing the configurations that we have, 3 ways of representing the relationships between points in a trajectory. We can provide coordinates for each of the points. So those are my capital X3, capital X2, and capital X1 has been skipped off for some reason. So we've got some sort of set of basis vectors, and we've got the projections on those basis vectors, the X1, X2, X3, and so on and so forth. So that's one way of representing our trajectory. A second way of representing the trajectory is we can take each of those points and we can calculate the distances between them, and then we would have a matrix of distances. So if we've got a trajectory with n frames, we've got an n by n matrix of distances between each pair of frames in our trajectory. So that's our D. And then the third way of representing the relationships between these points is that you can have a matrix of what are called kernels. And these kernels are the dot products between those sets of basis vectors. So the x1, the dot product between the coordinates of one point and the coordinates of another point. So once we've got this trajectory, we have these 3 ways of representing it. 2 of them involve an n by n matrix, the n by n matrix of kernels, or the n by n matrix of distances. And then the third involves a series of projections on basis vectors. And the nice thing about thinking about it this way, so like I said, we've got the coordinates of points, we've got the matrix of distances between points, and we've got this matrix of dot products between these points. So the nice way of thinking about it this way is, this is the representation of the projections of these points on our basis vectors. So here we've got the coordinate of in the row, we've got the coordinates of the first point, okay? And then in this row down here, we've got the nth coordinate for all of the points, okay? So we can construct this matrix that contains all of the configurations in our trajectories. So in the columns are each of the trajectory frames, and the rows are each of the coordinates, okay? Now, if we have this matrix and we multiply that by its transpose, what we get out is the matrix of dot products, so this matrix of kernels, okay? And it also turns out that we can calculate the matrix of distances using from this matrix that contains all of the points, using some simple matrix algebra as well. And what this means is that these three representations that I talked about, this matrix of kernels, the matrix of distances, and the matrix of all these projections on these basis vectors, are equivalent, and we could convert between them. And that's the basis of these linear dimensionality reduction methods, PCA and MDS, basically, okay? Is that you can convert between these different methods. Now, I don't want to talk about this too much because there was loads of resources that you can find that will explain these ideas. As I can give you notes that explain these algorithms and that you can work through at your own pace, with whatever pace you feel comfortable with matrix algebra, okay? So that's the idea of those linear dimensionality reduction algorithms. Basically, in most of them, when you're doing these linear methods, what you're doing is you take a matrix and you find the eigenvalues and eigenvectors of the matrix, okay? So it's just diagonalizing matrices. And that's all Plumed is doing to construct these representations, which is nice, okay? And that's the linear idea. The nonlinear method we're going to talk about is this sketch map method. That's a method that Michele Ceriotti and I developed. So the idea with sketch map is you've got some high dimensional representation of the data, you've got some, and you want to find some lower dimensional representation. And the way that you do this is you minimize a stress function. So you try and reproduce the distances between the pairs of points. So that's the same as what's done in multidimensional scaling. But the difference for sketch map is that instead of trying to reproduce the distances directly, you try and you transform the distances by a sigmoid function, which basically ensures that points that are close together are just projected close together. Points that are far apart are projected as far apart as they need to be. And the algorithm focuses on reproducing a particular set of distances that you're interested in. Okay? And again, if you're interested in these methods, I would recommend going back to the literature and reading those papers that go through this nice and slowly and at your own pace. And those resources are available in the tutorial. In the tutorial itself, what you'll do is you'll apply these three different methods to some trajectories of a protein. And what I think you'll conclude, and I'm willing to be proved wrong on this one, is that you're not actually getting that much more insight by running these algorithms on that data. You know, the machine learning hasn't found you a particular, just because you've got a low dimensional representation that you can visualize doesn't mean that you have a particularly better understanding of the problem. So I've seen that someone's just posted in the chat. Is that a question or a comment? If you want to, whoever it is, if you want to give your comment now, rather than using the chat, it's difficult to open with me in presentation mode.
Oh, yeah, I was asking a question like, could you like provide the paper proposing the sketch map method, or is it provided in the tutorial?
Yeah, it's provided in the tutorial, I think. I will double check that it's there. There's
Okay.
actually, there's a longer, I didn't provide the original paper, but I provided a longer paper that I wrote, which is actually a chapter of a book that explains all of these methods.
Sounds good. Thank you.
So that you can have a read through that, and it should have references to all the original literature as well. Okay, great, perfect. So let's summarize what we've talked about. So in terms of this tutorial, what we're going to do is we're going to learn how to do Plumed with Python, so how to call Plumed from Python. We're then going to learn how to construct these chemiscope representations. We're then going to have a go at these various different dimensionality reduction algorithms. And for all of these dimensionality reduction algorithms, you're going to construct a chemiscope representation and try and see if you can make head or tail of what these algorithms are showing you. And I think you're going to conclude that none of these CVs are particularly physically meaningful. They're not telling you anything about this particular problem of what's going on in that trajectory. So let's get to this question of how to construct CVs that are physically meaningful. And trying to talk about how to do this perhaps a little bit more systematically. So how can we go about constructing a CV in a sort of systematic way that might be generalizable to lots of different problems. So let's go back a second and apply this to, rather than applying this to some complicated physical system that we might study in research, let's apply this business of constructing a CV to a really simple problem that would be on an undergraduate statistical mechanics syllabus. So the problem we're going to look at is the good old lattice gas Hamiltonian. So what we've got is we've got a bunch of spins that can be in one of two different states. They can either point upwards, aligned with a magnetic field, or they can point downwards. So each spin can point up or down, and they have a lower energy when they point up because the magnetic field is in that direction, and these spins are non-interacting. Okay? And what you, perhaps unsurprisingly, if you have n of these spins, the lowest energy state that we can have has all of the spins aligned with the magnetic field. That's lower energy than anything else, okay? And hopefully when you did undergraduate statistical mechanics, you studied systems like this, and you understand the behavior of such systems. For those of you who, if you don't remember what you studied, I've got a little recap here in this figure. So what I've got in this figure is I've got 3 slides. I've got the middle slide shows the average energy as a function of temperature, the middle panel for this particular system. The panel on the left shows the probability distribution, the marginal probability distribution as a function of the energy for a particular temperature. And it's the temperature indicated by the red line. So the red dashed line that comes across points to the appropriate temperature point on the blue dot middle panel. And then on the right, I've got the density of states, which is the number of states with a particular energy, okay? So this sort of system, if we heat it up, this is what we see happens to that probability distribution. What you see is, as we heat it up, the average temperature goes up, and our distribution comes to resemble the density of states more and more closely to the density of states. And what's happening is, remember, within statistical mechanics, the probability of being in a state is the exponent is proportional to e to the minus the inverse temperature beta multiplied by the average energy. So as we increase the temperature, the differences in energy make less and less of a difference, and what matters is the entropy, okay? And the entropy is just related to the number of states. So what we see is that we go up in temperature, the distribution, the distribution of probabilities of being in each of the microstates comes to resemble the density of states, the distribution of energies, more and more. So that's what happens in these sorts of physical systems. And so you see this transition from at low temperature, all the spins want to be aligned in the field because their energy is really important. But at high temperature, the spins, we want to have a state where we have an equal number of spin up particles and an equal number of spin down particles, because most of the configurations have equal numbers of spin up and spin down. Okay, so that's a sort of model system that is useful to think about when you're thinking about how we go about constructing these CVs. So we're going to have this transition that's going to take place as we increase the temperature. And we might ask ourselves, well, what could we use as a collective variable in our language of these MD simulations to understand the behavior of such systems? And the answer to that is we can just use the distance from that lowest energy configuration. Okay, so we're just going to use the distance from the lowest energy configuration. And what we should see is that at low temperature, when we're in the lowest energy configuration, the free energy is lowest when we're close to that point. And then at higher temperature, we should see that a minima appears far away from that point. So let's have a look at those free energy surfaces as a function of the distance. So just the sum of the squares of the differences between those configurations from that lowest energy configuration. Okay, so I'm going to use that distance. And this is what we get. So we get exactly what I said we would. We have that at low temperature, there is a minimum at d equals 0, which corresponds to having all the spins ordered. But at high temperature, the minimum shifts to some higher value because we want to have about half of the spins aligned against the field. So this is always, if we know that one configuration is lower in energy than everything else, and that there is one particular lowest energy configuration, we can always use the distance from that configuration as a collective variable. If the problem is just what, this is the lowest energy configuration and everything else is uninteresting, we can always say, well, what's the free energy as a function of the distance from that low energy configuration? But if we have a free energy landscape that looks like that just has a single minimum, single funnel, goes down to a lowest energy state, there's possibly not any point in doing these free energy methods, because we can simplify this down and we can simply say that all of the fluctuations around that point are harmonic, and then we can use the harmonic approximation to calculate the free energy of that state as a function of temperature, and everything comes out analytically using the maths that you learn from undergraduate statistical mechanics. So here I've got, assuming it's a harmonic approximation, this is what would happen to the probability of being the density of states as you increase temperature in that case. It's an easy problem. So for those sorts, if you really have a problem where it's just a single minimum and you're interested in a single minimum and what's the free energy of that single minimum, free energy methods maybe are not the right way to go, because as I say, you can use simpler methods and you can use analytic maths. You can even incorporate the quantum effects within such methods, because you can solve the harmonic oscillator, including quantum mechanics. So when do we need these free energy methods? We need free energy methods when there are metastable states. And the important thing here is the plural, that we have multiple states and we want to calculate the relative free energy between them. If we've just got a single state, like I said, we can do some simpler method, well, notionally simpler, like harmonic or quasi-harmonic approximation. But if there are multiple states and we can't calculate the relative free energies of those multiple states, then that's when our free energy methods come in useful. Okay, so here's something that should be very familiar by now. This is a free energy landscape for good old alanine dipeptide, and this shows that this is a free energy surface that has two of these metastable states. So we've got two distinct basins, the C7EQ and the C7AX, which are these two metastables. We want to calculate the relative free energy between those two states. Okay. Now, what we don't want to do here is we don't want to just use the distance from one of those states as a free energy coordinate, as a collective variable, because we know that there is this other state out there, so we should probably take that into account. So the simplest thing that we can do is we say, well, the C7EQ state is over at some point x1, and the C7AX state is at some other point x2. And we can thus calculate the vector that connects those two configurations. So that vector is shown as that black arrow. Now, if I then have another, so that's x1, that's the start of that vector, and x2. And those can be coordinates in a space of any dimensionality, up to the positions of all the atoms. Okay? Now, if I then have my position here at x3, what I can do is I can say, right, I'll calculate the vector that connects x3 to x1. And then once I've done that, I can calculate the projection of that vector onto the vector connecting those two states there. Okay? And that's very simple pre-university maths. Hopefully you all know how to do that calculation with vectors yourself. Just in case you don't, the appropriate calculation of the collective variable there is you take the dot product between x2 minus x1, so that's the vector connecting the two states, and the vector, the vector that connects the two states, and the vector that connects the initial state to the current position, so that's x3 minus x1, and then you divide by the magnitude of x2 minus x1. Okay, so just using simple vectors projections of these points. Okay, and that's a perfectly adequate CV to understand the transition between those two states. Okay. Now, you can use this as your collectible, and I think for this system, it probably will work fine. You'll probably get out perfectly good free energy surface, and you can reweight on whatever collective variable you want by doing this. If you want to be a bit more refined, you can extend this by saying, well, if I'm going from here to here, what I'd really like to be able to do is take this path that's shown there. And instead of having the projection on one single vector, I can have the projection on these two vectors here, because I know that that point at the transition state one, because that's probably the configuration that I'm going to go through as I move from C7EQ to C7AX. Okay, so you can do that instead. Same idea. You basically take you just take projections on multiple different vectors there. And if you take this to its sort of logical extreme, what you get to is the idea of a path collective variable. And a path collective variable is just a saying, okay, I want to pass this particular set of waypoints in this particular order, and you have some collective variable that takes you along that path that is somehow representative of the transition between the two important states. And in partial answer to this question of what's the difference between a collective variable and a reaction coordinate, I think this is the way that some people in the literature think about this distinction. So the collective variable is any any variable that you can think of, whereas the reaction coordinate is more of that sort of pathway that connects the two different states. So you're trying to refine that pathway and find what the actual route that is taken during the reaction, although there are multiple routes because it can take many of them. So this path collective variable idea, which is explained in the tutorial, allows you to build on that sort of framework. Okay, so let's just...
Okay, thank you very much.
No problem. I'm getting to order parameter in a minute. So let's summarize what we've talked about in thus far that you're going to do. So first of all, looking at how to call Plumed from Python, then a little bit about how to build chemiscope representations, then this issue looking at the dimensionality reduction, and then you go through and learn how to calculate all these various different kind of systematic CVs that I've talked about. So how to calculate the distance from a configuration, how to calculate the projection on a vector in some space, and then building that up to the path collective variables, all for this alanine dipeptide example. Okay, so those are the first bits of the tutorial, and then the last sort of topic that I wanted to cover concerns a problem that comes up quite often if you're interested in solid state systems, which is the issue of indistinguishability. So if you've got multiple atoms that are of the same type. So here, for example, I've got a solid and it's solid sodium chloride, and we want to build a CV that knows that all of the green atoms are the same, okay? Because we know that if we have a solid liquid transition, for instance, we know that it doesn't matter which atoms go through the transition first, all of those pathways are the same. So we can't treat the atoms as distinguishable like we would do if we were doing biophysics. We have to take into account the symmetry somehow. And I'm going to show you, in the tutorial, I show you a particular way of doing this. And the way that I'm going to show you argues that thinking of this in terms of building a CV that knows that all the green atoms are the same is not the right way of thinking. I think it's not the right way of thinking about this problem. So the way I would think about this problem is that you calculate an order parameter for each atom. So now we're getting to the third of those terms that we've seen. So each atom will have an order parameter, and that order parameter is going to tell you whether or not that atom is in the solid. So is that atom solid-like or liquid-like, okay? And it's going to quantify that for each of the atoms in your system. And what this means when you calculate this order parameter for each system is that we can take one configuration and we can calculate the probability distribution for the order parameter in that one system, because we have multiple instances of that quantity, because we've got one instance for each one value of the order parameter for each atom in our system. So chemiscope allows us to construct these representations, and we can see what the order parameter is for every atom in our system. Okay, and we can now look at both what happens in terms of different frames. Instead of each frame being a distinct representation of that collective variable, there are multiple values of the order parameter within each frame because we have one value for each atom. Okay, so I will show you how to construct this chemiscope representation where you have these multiple quantities per frame as well. A nice thing as well is that we can then calculate the distribution of those order parameter values, okay? And this is the distribution that we get for the particular system that I'm showing in that chemiscope representation for 3 particular order parameters, okay? Now, if you look at that chemiscope representation, hopefully you can see from the figure on the right that you've got part of the system is solid-like and part of the system is liquid-like, Okay, so you've got a solid-like bit in the middle where you can see that the atoms are ordered, and you've got a liquid-like bit on the edges. And when you look at the distribution of order parameters, you see that in at least two of those distributions. So in the middle panel of those middle distribution there, you see that there's the distribution is bimodal. So you have a peak at 0, which corresponds to the value of that order parameter for the liquid, and a peak at around 0.7, which corresponds to the value for the solid. If you look at the panel on the rightmost panel there, you see that there's a peak at 0, which corresponds to the liquid, and a peak at 1, which corresponds to the solid. That's the panel that's labeled transformed FCC order parameter. Okay, so the nice thing is that for each configuration, because each configuration contains multiple atoms, and we have one value of the order parameter for each atom in the system, we can always calculate those distributions, okay? And we can see that the peak for the solid and the peak for the liquid, okay? And that's our distinction between our three things. So we've got collective variable, which is just some coordinates, so some linear or nonlinear combination of the atomic configuration. We have reaction coordinate, which is the pathway that the reaction actually proceeds via. And now we have order parameter, which is some usually function of an atom or a small number of atoms that we have multiple instances of in each trajectory frame. Okay?
Okay, thank you.
No problem. So if we have these distributions, though, there is a question. There's a nice thing. If we think about these distributions, whenever we've got a distribution of quantities that are indistinguishable, the negative logarithm of these distributions multiplied by KBT is a free energy surface. So by taking one configuration that's equilibrated, if we have these order parameters, that we can calculate a free energy surface without doing an AMD. We can calculate an estimate of free energy surface by having an equilibrated configuration. So in theory, if we're looking at these order parameters, we can converge our free energy surfaces much more quickly, because we can look at the relative free energies of the solid and liquid. So by taking the negative logarithms of those distributions, we can get the relative free energies of the solids and liquids from those distributions there, which is kind of cool, without doing any MD or doing considerably less MD. But if we're interested in looking at nucleation or some problem like that, what we generally want is the number of solid atoms, okay? So how do we go from these distributions to a measure of the number of atoms of solid? And this is where we need to be careful, because we need to be much more careful about how we define what that question means. So what does it mean for something to be a solid? And the way that I would define this is that you say, right, okay, I have a system that contains n atoms, and I'm going to say that these atoms are either solid or liquid. So my atoms can only be in the solid or in the liquid. They cannot be at the interface or anything else. So the total number of atoms in the system is going to be equal to the number of solid atoms plus the number of liquids, okay? And then what I say is some extensive quantity, capital phi, is going to be equal to the number of solid atoms, and that extensive quantity is going to be calculated by taking the sum of all of the order parameters for all of the atoms in my system. So that's very easy to calculate. I calculate each of these order parameters for each atom in the system, and I sum that. But before I've done my simulation, I'm going to do simulations of the solid and the liquid, and I'm going to calculate the average value of the order parameter in the solid, and that's going to be that capital phi s. So that's the average per atom value of that quantity in the solid, and the average value of that quantity in the liquid. And then what I'm going to say is that the contribution that each atom, the contribution to phi is only made up of a contribution from the solid part of the system and a contribution from the liquid part of the system. So that quantity, the sum of all those order parameters, is going to be equal to ns multiplied by the average value of that order parameter for the solid plus nl multiplied by the average value of that order parameter at the same conditions for the liquid. Okay? And then what I've got is I've got two simultaneous equations, one for n and one for capital phi, and two unknowns. The two unknowns are the number of solid atoms ns and the number of liquid atoms nl. And I can rearrange and solve for those two quantities, and I can get an estimate of the number of solid atoms that way. And when we do it that way, what we're doing is we're carefully defining what's known as a Gibbs dividing surface. And we're making clear how we made that assumption. Saying this particular, when we do this, we're saying, I am going to have zero what's called excess for this particular extensive thermodynamic quantity, capital phi. And the neat thing is we can do this with any extensive quantity, and any sum of order parameters is an extensive quantity. So in the exercise, I show you how you do this for the three different sets of order parameters up there. So this black line gives me the number of solid atoms, assuming that the coordination number provides me a good description of the difference between the solid and the liquid. And you can see that distribution isn't bimodal, but I can still do this procedure of doing the Gibbs dividing surface. You can do it using this S order parameter, and that gives me this red line, and you can do it using this transform one, which gives me this green line. So you do different estimates for the number of solid atoms if you use these different order parameters to make the calculating this in various different ways. Okay, so those are the exercises that those are the exercises for this week. So to summarize again, how to call, so we start off by looking at how to call Plumed from Python so that you can do all your experimentation within a Python notebook before you run your simulations. Then we're going to talk about how to use the chemiscope to generate these nice representations where we can visualize what our collective variables are. Then going to have a look at the dimensionality reduction issue and see how to do dimensionality reduction with Plumed. Then looking at those systematizing collective variables, so using the distance from a configuration, the projection on a vector, path collective variables, and so on, and then finish off with this little bit about dealing with systems where you've got solid and liquid, and you want to calculate the number of solid atoms and developing collective variables for that. So as always, the exercises are in the same place as they always are. So you go to the Plumed website, go to Masterclass, click on the topic of class 21.6, it should be, which is dimensionality reduction, as shown there. Questions and discussions should be available in the Slack channel Masterclass 21.6, obviously. And this video will be available on YouTube, so you can watch it again if you think it's useful. Or the risk should be there within the masterclass, so you can read around these various different topics that I've talked about in broad sweeps here. So with that, I think that's all I had to say. So let's get back to here. Does anyone have any questions about any of that? I know I've gone over a lot of material very quickly, but hopefully by working through those exercises, you will make more sense of it, and also by asking questions when you have them on the Slack channel, we can address the concerns that you have if you have them.
Oh, excuse me. I kind of have a logistics question about
Yep.
masterclass. So, like 2 weeks after I see that there is a poster session, but I was kind of wondering like how that will be going, or
Good question. So I think Giovanni has a better idea of how that will work. I think we're going to use some software which allows a kind of more, it sort of allows people to virtually walk around different posters. But I haven't done this before. Giovanni swears to me it's brilliant. But we will give you more details nearer the time. So
Okay,
only a
that's
partial
good.
answer.
Thank you.
But make a poster as you would normally.
Okay,
Even
thank
if
you.
it's just a few PowerPoint slides, it's also fine. Does anyone else have any questions about the material?
I have a question.
Yes.
Maybe I don't know if I understood. So a collected variable can be any variables or any combination of coordinates, so whatever you want to define. But it makes sense to define, for example, an ordered parameter that is not able to distinguish between states. So because you can define a collected variable as the one that you show at the beginning, that you have in X, let's say you have only one well, but in Y you have two well-defined, two wells. But it makes sense to define an ordered parameter that is not able to distinguish between the states.
So not really, no. So this language of order parameter, if you look at the sort of history of this, the language of order parameter comes out of work by people like Landau and theories of phase transitions. And so the way that I like to use it is this notion that we've got multiple indistinguishable representations of our physical system within a single trajectory frame. So we have an order parameter for each of the atoms, and that order parameter is in some sense, the distribution as a function of that order parameter is bimodal. Yeah, so we can calculate the value of this quantity for each of the atoms in our system, and some will fall in one bin, and some of the configurations will form in a second different bin. Some of the atoms. And that's what I mean by order parameter. Whereas collective variable would be for systems where you don't have that symmetry, like proteins, where when you run your MD trajectory, you have one representation of the protein in general. And so your instantaneous, you just have one collective variable value in that configuration.
Perfect, it's clear.
So yeah, I think this is a really interesting, thing about this sort of where this whole topic of MD simulation comes from. So if you think of what we call traditional statistical physics problems, they were things involving things like solids and condensed matter physics. And in all of these problems, you have loads of symmetry to help you with thinking of appropriate order parameters and constructing theoretical models. Whereas the sorts of new things that people have started trying to simulate are things like proteins, where you don't have that symmetry to help you out. And this also plays into why people are using these machine learning algorithms, because we don't have all of this mathematics that is built on symmetry really to help us with these problems. So we have to use these very general models to construct these representations of these problems when we don't have symmetry to help us out. Yeah, so and it also answers the questions, why are physicists interested in proteins? And the reason is because these are difficult problems, because we don't have a lot of the traditional tools that we would have as physicists, as theoretical physicists, to solve these problems, as well as all the altruistic stuff about, you know, proteins and so on, and human beings being made of them and so on and so forth. But really, it's that they're difficult. Does anyone else have any question? I am the host now. Okay, great. Okay.
I could make a last question, and sorry.
Yeah, no problem.
So how to measure this quality of the CVs? So because you know, there is a metric that you can say is suitable to say this could be a better collected variable. That's this other one.
Okay, so this is this comes to your, you know, this comes to your research question. So what we're going to suppose is that you know what your question is. So let's suppose that you're looking at a typical protein folding problem. Okay, so if you're looking at a typical protein folding problem, a nice thing to get for a paper on this is going to be a free energy surface as a function of the radius of gyration and the distance from the folded state. Okay, and that's going to be a nice thing that you can put in your paper that people understand, and they understand where that figure is coming from, and they can make sense of it. Now, you might not bias those CVs. Okay, you might bias something else. But the goal is to get out that free energy surface. As well as doing, so what you're then going to do when you do your simulations is you're going to see, okay, the first thing to try is I'm going to just bias the distance from the folded state and the radius of gyration. And probably what you'll find is your metadynamics, or whatever method it is, doesn't really converge. So when you do all your error analysis and all of these things that we've taught you, everything comes out as a mess. So then you go and you refine your CV and you come up with something better. You run your calculation again, but you reweight onto the free energy, onto the radius of gyration and the distance from the folded state. Because ultimately, that's always what you want, because that's the thing that allows people to make sense of the data that you're generating. So I'm in the process of finalizing a paper at the moment, and you know, we study a protein at the end of it, and the CV that we're using for the metadynamics is some 6-dimensional combination of torsions, and there's all sorts of Gaussians and all sorts of stuff going on in there. It's really very complicated. But what we put in the paper is the free energy as a function of basically the distance from the folded state and the radius of gyration, because that's how we understand protein folding. You know, the proteins, when it's unfolded, it's lots of open and floppy. It doesn't have a lot of its native contacts, but when it's folded, it has its native contacts, and it's compacted. So it's your CV. Your CVs are what are allowing you to construct that understanding of what's going on. Does that make sense?
Yes, it makes sense. But I was thinking that, for example, people propose that the perfect collected variable should be the committer and things like that. But I don't know if that is true. So, or if there is any other way to measure the quality of the collected variable.
I mean, you can calculate the committer, but you know, and in fact, in the tutorial, I should have mentioned, I show you how to calculate the committer for some of these different variables. And you can absolutely do all of that analysis, but is it really telling you anything? Is it giving you more insight by having that information? Is it telling you something new? And the answer in a lot of cases is no. What you want is I want the relative free energy of this configuration and the relative free energy of that configuration, because maybe this configuration binds better to some ligand or other. So I want to know how much of that is typically going to be present when I'm at equilibrium. So the question, the CV is the heart of the question that you're asking. So, there's kind of like these two sort of factions is not the right word, but these sort of two ways, I think, of thinking about the sorts of papers that people write in this area. There are the papers about methodology, where people are developing methods to solve problems that normally have been solved before. And a lot of the sort of the discussion in those papers is really about using what we know about these systems to demonstrate that those methods are working. But what we know about those systems comes from other people doing simulations. And then there's the other sort of hand, which is people doing applications of these things. And often, you don't really need some very sophisticated CV, because you've got some idea. If you've got some application in mind, you've got some very specific research question that you want to answer. And that very specific research question is telling you what CV you should use. So, and normally having the ISO committer is not giving you necessarily a better answer to that very specific research question. Does that make sense? I'm going to take that resounding silence as that point was so profound, it's just stunned everyone into silence. I forget that this thing is recorded on YouTube, and they're talking nonsense at the end of it. It's probably undermining my reputation. Never mind. Okay, great. So, as always, if you have questions, please do ask them on Slack. I will try and respond as quickly as I can. Like I said, next week, I can show you the solutions to we'll quickly go through the solutions to the exercises, but I'll also put full solutions and full notebooks online so you can go through them at your own pace. I don't really want to spend too much time on that. What I'd really like to do is hear about the things that you're working on and what ideas you have for what CVs you might use to study those systems. And we can talk about that. Now, obviously, I understand that you probably don't want, if you're talking about the research you're doing, you don't want that streamed on YouTube. It's fully understandable. So we don't have to stream on YouTube if you don't want to, but we'll sort of work out what to do next week. But do try to have a think about, how am I going to apply this in my own research? Because if you're here and you're not trying to apply some of these ideas in your own research, then what's the point? Yeah. Okay. So next week we try and have a chat about what you're doing and these sorts of things, as well as going quickly through the solutions.
Okay, thank you very much.
No problem. Bye-bye all. I'm done.
Thank you, Garrett.
No problem. Thank you.
Bye.
Thank you.
Bye.
Bye. Thank
Bye.
you.
Bye.
Okay.